Welcome to our webinar, and hello to everyone who has joined us. My name is Jason Wilkinson, and I will be the host for today. Before we get started, there are a few things to note. First, this is a live webinar, so if there are any questions throughout the presentation, you can ask them in that Q&A section. There's little buttons at the top where you can ask questions. We also have Jason Orr, one of our experienced engineers, on chat to answer questions. So, and if we don't get to them during the presentation, we can probably address them afterwards. Also, if you have any feedback or about the content or the platform we're using or anything else, we'll have a survey at the end that you can fill out. We're trying to do one of these webinars per month, so we have other topics that we will be talking about coming up, things such as interconnect with automated test systems and hardware abstraction layers and things like that. So look forward to that and look for those invites. Next, I would like to introduce our presenter for today. His name is Alex Hudson. He has a degree in computer engineering and is a test stand training architect. He is in charge of training and onboarding here at Tesseract. So that gives you a bit, the seminar should give you, the webinar rather, should give you a bit of a taste of what some of our training is like. So with that, I'll hand it over to you, Alex.
Thanks, Jason. That's a great introduction. I have my own introduction in my slide deck, so I'm going to make you go through that as well. So I'm going to turn off my camera because I can put myself in the slide deck. So this is me. Hello, I'm Alex Hudson. I have a bachelor's in computer engineering. I am in charge of training here at Tesseract. I started at Tesseract just over 2 years ago, and I've done onboarding for most of the Tesseract employees here. We've grown to 40 employees, and I've done a bunch of training externally for a lot of different organizations on the framework, which we're going to talk about a little bit today, and talk about why we use a framework. I've spoken at NI Connect with Sam Roundy on building a good test team. And then I used to teach AP programming. I used to teach Microsoft Teams. I love roller coasters. 10 points if you can name the roller coaster behind my picture. And then I really hate boring slide decks. So if you get anything out of this, I at least want you to be somewhat entertained. So there's one more thing that I really just want to set expectations with. This presentation is tailored towards high-level software ideas. We're not going to go in depth, and we're not going to talk a lot about hardware. Hardware's fairly concrete. You get a pretty robust data sheet, and you get the benefits of any partner that you're using, Keysight, NI, whoever. They're going to help you out a lot. So hardware is not going to be the focus of this presentation. It's going to be more software focused because there's a lot of different ways to approach software. So I just want to set that expectation so that I don't want you to feel gypped like we didn't talk about hardware at all. So there's that. All right, so let's actually get started here. So we're going to talk about, I did not go to school for this. So I studied computer engineering. I did not study test and measurement. I'm sure that's probably the case with most of you. I think there's maybe 1 or 2 schools, Texas A&M, that teaches test engineering as a degree. And then why does everything keep breaking? Oh, great, another framework. We're going to talk about what framework means, why I'm talking about the term framework. And then we're going to talk about key components of an automated test system. And that's really the meat and potatoes of our presentation. And things to think about, both from a software perspective and like a process perspective. Then finally, we're gonna wrap it up with some recap and questions. Feel free to ask questions again through the Q&A and/or chat throughout the presentation. Jason should be able to answer any of the questions that you have. And Jason Wilkinson can pause me if I'm going too fast on any of the topics. So let's get going. We are test engineers, and we need to develop a test station. And our test station is going to look like this. So how did we get here? And how do we make a test station like this? Well, we got to start with where we're at and what we need to do. So we're going to start with the DUT. This is our device under test. And this can really be anything. We test a lot of things, anything from glue, stoplights, random pieces of hardware, something that flies. Really, at the end of the day, we test everything. And what that really makes us feel like as engineers is that we need to know everything. Test engineering is really difficult because we need to know a lot about all of the components around the DUT. So I and most of you are probably only formally trained in one. So you probably only went to school for one of these things. And oftentimes it's not computer engineering. I think I benefit greatly from having a computer engineering degree in the test and measurement world. But when I got tasked to test glue, I had to learn a little bit of chemical engineering. So we don't know everything, but no worries. We will learn as we go. We always do because we're good engineers, right? We learn the pieces that we need to accomplish our task. And we get really good at this. And we learn all the pieces that we need to know to build a test system. So we build a working test station, and it's perfect. Everything's working. It's flawless. It's got no problems until the requirements change. And they go, hey, we actually need you to save these results to the database. And don't worry, we've already defined the schema for you. But then you're sitting there and you're looking at the schema and it has nothing to do with the same test process that you're following. So you have to do a whole bunch of hokey things, but no worries. We use some duct tape and we find a solution. And good news, we build a working test station. It's a little bit jankier than it should have been because we've made some changes that weren't planned for because requirements changed, but it's working. However, we get in this cycle of requirements changing, and then it turns into a real maintenance nightmare. And in my opinion, maintenance mostly comes down to good software. So we can solve some of these problems, and it starts with software. And the reason I'm hitting software so hard is we are automated test engineers. We are making an automated hardware test system. And that's really the key. So really, we're not test engineers. We are now, and I want you to get in this mindset of software engineers that specialize in test. Right? We're good at understanding all the other pieces, but really we need to be good at writing robust software to make our test systems more maintainable and easy to use. So going back, we need to develop a test station, and this time as a software engineer. So we can take the approach of we learn as we go, but no, we're not going to do that. Lots of test engineers just go for it, and they learn as they go, and they make things better and better, and they iterate just like any good engineer. But they don't typically attack it with a plan. So they just kind of throw things together. It kind of turns into a jumbled mess. Here at Tesseract, we use a framework, and you should too. So we're going to talk about why we use a framework and what a framework is, what that really means. Because framework is an incredibly loaded term. So let's take a little bit of pressure off of the word framework. Framework is just a basic structure, plan, or system of concepts, values, or customs and rules. Basically, it's a game plan that everyone follows, and it has designed rules within it. And these rules allow us to make assumptions, and they allow us to quickly find solutions within that framework, right? So it's also really important to know that frameworks can be made up of other frameworks. There are frameworks for everything, right? There's SMART goals. SMART goals is a framework. So you might have a product strategy framework that has a scorecard that has to do with KPI and a feedback form that are each their own frameworks, and you have total cost. It's really, you should build your framework off of existing good ideas or add new existing good ideas. And so I don't want anyone to think, oh, if there's a framework, we have to do it that one specific way. It's a set of rules and customs so that you have a defined way of doing everything. So using a framework should provide several benefits. It should make you quicker and more productive. It should add consistency to your software, so you can go look at a brand new test station you've never seen before, and know what to do. You should be able to reuse code to increase rapid development. It should be easy to support, again, because you know where everything is. And it should be able to scale. You can't have a framework for one problem. You should have a framework that solves multiple problems. Well, multiple problems within one big umbrella, right? So what is a good framework? A good framework should check all of these boxes. You should have defined components and conventions. Defined components and conventions means I have these big core pieces of my framework. These are really important. These are how they interface with the next piece, and these are the rules with interfacing between them. You also have rules regarding style and how things are done within the framework. So then your framework also needs to be modular, flexible, and extensible. So what that means is you need to think about how is this going to scale for things that I haven't accounted for? Can it? And do we want to plan for it? Most of the time you do want to plan for it, but there are certain circumstances where you go, nope, our framework won't work for that. That's okay. Don't do it in your framework in that case. Don't bend the rules of your framework to make something work. But ideally, your framework under its umbrella should be able to solve any problem within it. And then if you have done those two things, you need to make it well documented and easily supported. You should start gathering, people should start buying into the framework and using it. And they'll start using it, which will make it more consistent and reliable. And if it is already consistent and reliable, they will continue to use it, because people will build trust within the framework. And really, all of this is mute if it's not useful. So it really needs to be useful. You need to solve an actual problem with your framework. Do we have any questions? Let me just look at chat, just to make sure I'm not missing anything. No. All right. If you have any questions about framework, why we use a framework, why you hate the word framework, let me know. But we'll go ahead and continue here. So, we are going to explore the TestRact automated test framework. Now, what that means is we're going to explore a lot of our stuff. If you don't have a framework, you can talk to us. We can sell you, or you can use our framework. We can figure that out. But you don't have to do it our way. What I really care about is you have a plan and you do it some way. You use a framework. Using a framework is just going to make your life easy, and using a good one is going to make it way easier. So here's a high-level overview of the TestRact automated test framework. You see we have our hardware on our left. Then this main part is all our software. We've identified 6 components as they relate to our framework, and 2 of them are not really even software. So step 1, we have a test station information document. This is how are we going to test it. This can serve as an architecture document. We'll cover that more. Then we have our entire software stack. And then we also think about deployment as part of our framework. And we have a plan for deployment from the beginning. Because having finished a project and then moving it to a bench and having none of it work is a real pain, and that is a bummer. So the 6 major components that we have identified as major components that you should probably think about having in your test framework is some sort of documentation for your specific project that is customized to your framework. And then you should have a hardware abstraction layer. This will help separate tests and GUIs from actual hardware, allowing you to swap hardware if you need. Then you need to think about what kind of GUIs are you going to have? What kind of views does the operator need? Is the basic view fine? Is a pre-built view fine? Is that not going to work? So you got to think about GUIs. And then you also have to think about the actual test you're executing. I know that one's a crazy thought. But we have rules around how we actually build our test sequences. And so you might like some of the ideas that we have there. Finally, you need to, well, not finally, sorry. final part of the software stack is identifying your data storage and your documentation and where everything for this is going to live. How are you going to look at data from your test measurements, that kind of stuff. Then finally, how am I going to move it or redeploy it if I need to? If the whole station, burns down in a fire, how are you going to get it back to where it was? If all of your code was just on that test station, you have a problem, right? So these are things that we need to think about. And within our framework, different components can be worked on at the same time. And we'll talk a little bit about why. Not all of the components, but some of them or most of them can be. So step one, and something that you always need to think about when you're working on an automated test system, is your test station information document or software architecture document or whatever documentation you're going to use to govern the development of your hardware or your test station. And things that you need to think about in this is, what hardware am I using? What tests to run? What are my reporting requirements? Am I going to log to a database? If I'm logging to a database, what happens if I can't connect to the database at that time? Does the test fail? Does it not upload data? What happens? What are my limits? Are there any edge cases? Is there anything that's particular about this one? Like, do I need to be checking a safety threshold to see if anyone crashes and then crosses it? And then how am I going to shut down the software gracefully and safely quickly? And then any other risks that might be associated with that. This is really where we benefit and we put on our test engineering hat. This is where we, again, have to think like test engineers. The rest of this is all software engineering thinking, but this is where we put on our test engineering hat. We really should think about the entire process and how it's going to work. Also, at Test Direct, we budget about we recommend budgeting about 10 to 20% of your time for filling out and planning this. The more of the test system that you can plan out in this phase is going to help you for planning, for maintenance, and making sure that your project is extendable. Do we have any questions about the test station information document? I hope you guys are all allowed to chat. That would be a real bummer if you weren't. If we have no questions, I'll move on. Okay. So after we've done that, after we have a game plan, after we've thought about our process and what we're going to do, one more thing that I'll add. The test information document really should be in line with your framework. So our test information document has a hardware section, a hardware abstraction layer section. It has a test sequences section. It has a GUI section. So like having these pieces is really important to think about within your framework, and it also allows you to templatize and have a lot of the work in filling out the documentation done for you and not have to do a ton of thinking. All right. So once you fill that out, we have the rest of our software stack. So we're going to start with the how. This is a hardware abstraction layer. I would bet that most of you are somewhat familiar with a hardware abstraction layer. Our hardware abstraction layer supports simulation and logging natively, so you don't even have to think about it supports logging natively. Simulation we support through swapping. It supports record and playback, shared connections, and then we have a whole bunch of tools around it because everything's built the same way. So we can abstract a lot of that and take away a lot of that pressure. So this is how our HAL is architected. I'm not going to talk about this super in-depthly because we're going to have a hardware abstraction layer webinar at some point. But our hardware abstraction layer is object-oriented based with a little bit on top. So we have a grandparent that's a device, and then we have our device type, in this case, a DC power supply. And then we have all of our different devices underneath it. So a Keysight or a NI power supply, whatever. And then we also include simulation. So we always build a simple simulation with any of our device types so that we can test if we don't have hardware right there available to us and make sure that the rest of our software stack works. I would really encourage you guys to take that idea with you if you have a hardware abstraction layer add simple simulation to it. It doesn't have to have valid data, but making sure that your GUI can run effectively without having hardware available is super nice. And you can make your simulation more robust if it needs to be. But all of that is our object-oriented based stack, and then we build a little bit of a wrapper on top of it, um, which is a API, and we have tooling for this that automatically gets generated off of our device type. And so we can automatically include logging and reference management and all sorts of stuff within that API really easily, and that's all done for us. Us as devs never have to think about the API. It's all made by a tool because every device in our HAL is built the same way because we use a framework. So using a good framework allows us to make some assumptions, which allows us to build tooling, which is very nice. So that's our HAL. I'm not going to talk too much more about that, but if we have any questions about the HAL, I'm happy to come back to it. So, also, again, our HAL is built on object-oriented programming, plus a little bit more, which can be seen as a framework, which is part of our bigger framework. Again, just driving that point home. So then we need to talk about GUIs. And we have kind of a main GUI that we use called Task. It's Tesseract Automated Solution Controller. All it really is a kind of a big window where we can plug in sub GUIs into it. This allows us to have a single user experience, so we can have everything have the same look and feel, even if we're using different GUIs across multiple projects. It allows we've made the GUI really configurable, and it can load specific like sub GUIs for a specific scenario. So if you were on a test bench and you're really early in your hardware development phase, you can test using a bunch of like manual GUIs that interface directly with hardware. Or if you're in the production phase, you can have a fully robust automated system that's running and checking all the hardware status. The other benefit of using of why we use a main GUI like Task is it keeps everything in the same application space. So if we're using hardware or hardware abstraction layer, we can pause our test sequence and we can go interface with hardware immediately after that. So that's one of the benefits of using everything wrapped together in one. And this is kind of what our task looks like. So on the left side, we call them modes, but all these GUIs, you can switch between different GUIs to get different views within the test system. And you can remove those or add those as needed. We also include like logging and that kind of stuff into our main GUI. But the nice thing is once you've made a GUI, especially like a DC power supply GUI, it's only built once, right? And then you can reuse it across multiple projects. And because the shell can be skinned, you can change the look and feel depending. So that's another thing to think about is how am I going to handle my GUIs, and how am I going to share hardware references? Hopefully your HAL handles it. If not, that's some other stuff to think about. And Tesseract, or the Tesseract automated solution controller or task is built upon Actor framework. We're not going to talk too much about that, but it allows us to have each GUI run independently without knowing about the other GUIs, unless you want it to, making it really robust. So that's kind of our main GUI. And those are the two pieces of bread for our main goal, or our main sandwich. 2 pieces of bread for our sandwich, which is test stand or test sequences. We are actually testing something. So how do we test things? So the meat and potatoes of our automated test system is the test sequencer. We use test stand. You can use any test sequencer. You can use an in-house test sequencer. We're not going to talk about test stand super in depth. What we're going to talk about is how we organize our test sequence files. And these are some ideas that you might be able to take with you to your test sequencer. What we do is we typically have one file where our test entry point is. This is our client file, and it does all the bench specific stuff. It does overrides and callbacks that it needs to do with the test stand engine. It sets up everything for a test to be executed on the test system. Then we have our test abstraction layer. We call it a TAL. And this is typically DUT specific and or test specific. So it's really just one specific test that you're running, and it only interfaces with submodules. And we'll talk about submodules in a second. And its main job is defining the input parameters and the limits. So if I'm doing a voltage test, I should supply what voltage it should be at, and then I should read back what voltage I expect, right? And then I calculate a measurement on that. And then the test module is the part of the test sequence that's actually doing the heavy lifting. It's the thing that's interfacing with the DC power supply and then going, hey, I need the voltage. But it does not take any limits. It calls external code, so like LabVIEW modules or Python or whatever. And so we basically have three major pieces. One sets up the bench, one defines the test. It's like a config file almost. It's really simple. There's not very little logic. And then we have our test modules, which run a specific test. Another way to think about this is if I was testing a series of laptops, right? I might have a test that gets the size of the RAM. And if I'm testing a 16 gig laptop, I would expect a 16 gig result. If I'm testing a 32 gig laptop, I would not expect a 16 gig result. The test module only gets the result. The TAL actually takes the measurement and determines pass-fail status. Hopefully that makes sense to everyone. But separating test execution from limits is a really good way to handle testing from a software perspective. So if we have any questions, ask away. Yeah, and then again, we use test stands. We use all the other test stand components. And again, that's its own framework. That then the test stand handles a lot of reporting for you. But you might need external reporting, or if you're not using test stand, you need to think about reporting. And this really is kind of part of the test sequencer. It's extended from the test sequencer, as you can see in this slide. Your GUIs really shouldn't be concerned about reporting. Your hardware shouldn't be concerned about reporting. Your test sequence really shouldn't be too concerned about it, except for it's what's interfacing with it. Ideally, you'll decouple reporting as much as possible. But when you're thinking about reporting, you're going to have to identify report formatting needs. Use out of the box if you can. If not, figure out what's going to work best for you in the easiest way. Build plugins if you need to. Turn on plugins and test stand. Really, here's a really good pro tip that I've learned while working here is, if possible, create a report from the beginning. Lots of times you finish the entire test sequence, you have a report built, and then they go, that's not what I wanted. And so if you can give them the report before doing any of the other development, they will have an idea of where you're going to go, and you can work backwards. So pro tip, if possible, create a report beforehand, before starting, and then you can work backwards to get all that result, all of that data. So they don't pull a switcheroo on you and say, actually, we want this all in a database. So any questions about that? Okay. On to our final thing to think about, which is deployment, and oftentimes forgotten about. The way that we do development in our framework is service-based. So the HAL can be deployed independently of task GUIs, unless, again, those task GUIs have dependencies on the HAL. But what that means is we separate all these pieces into different packages. So we'll have like a HAL, we'll have a DC power supply package, and we have a test stand package. We don't put all of this together in a big monolithic build. And the other thing is we always develop against built code. So we are building hack project libraries as we go. The reason we do that is so that our code doesn't change when some other dev starts working on it and breaks things for us. It allows us to have more robust deployment when we develop against built code. And so anytime we make updates, we put those into a package. That package we use NI's tools, so it's an NI package, and we use that to put our PPLs where they belong. And if you aren't familiar with NI packages, it's really just a self-extracting zip file. It contains a payload, and it contains the destination where that payload should be, and it puts it there. So using some sort of tool like that to get things where they belong so you don't have dependency issues will make your life really easy. Because we're using NI packages for a lot of this, we can make assumptions. So NI uses feeds, so we can use a feeder solution. And then we've built some tooling around this as well, so we can validate our package state. We can easily go grab a whole bunch of packages at once and build kind of our deployment version of the entire test system and then install it with one click, even though it's made up of a whole bunch of little packages. This allows us to pick and choose what we need. So if for whatever reason a breaking change was made to a DC power supply, we could just choose not to accept that DC power supply breaking change. If you're working against not built code or not, released code, you don't get that luxury. So I really recommend having builds for the pieces of code that you're working on. That way you can always get the test station into a good state. So deployment is really something that you should think about. Think about how, once it's done, making sure that nobody can break it. If they do break it, how are you going to go back to the correct state? How are you going to validate that it's still good? Those are things to think about with deployment. Any questions about any of this? Okay. So that's really, I mean, we've blown through this. We've gone quickly. So we're going to recap just for anyone who joined a little bit later. We are test engineers, and we test not just a lot of things, we test everything. I have had to test glue. I have had to test things over an acid bath. So we test everything. And because we are automated test engineers, everything we test goes through software. And so at the end of the day, we really need to be good software engineers. That's going to make our life really useful. And so good software engineers benefit from using a framework. Again, you don't have to use the one that we just talked about, but if you implement your own framework, it should be efficient and it should increase productivity. It should be consistent. You should be able to reuse pieces for rapid development. It should be easy to support the way that the pieces interface are defined, and you have a plan for that. And then it supports scalability. So our HAL supports scalability through a plug-and-play architecture with object-oriented programming. Our task, so our main super GUI, supports scalability by allowing you to plug in different GUIs that you've created. These are all things to think about as you are developing a automated test station. So we really recommend including these kind of core components: a standardized documentation, a game plan, something that you get that gets filled out beforehand, that you can stick to as your Bible. Obviously, things are going to change, scope's going to creep, whatever. But have a plan that defines at least your main components and how they're going to interface with others. Then, once you actually get to do the fun part and start developing software, think about having a hardware abstraction layer. Think about being able to swap devices. Like, what happens if my key site goes bad and I can't get this key site DC power supply anymore, and I have to go get an NI one, and the drivers are completely different, and I have to rebuild my entire stack? No, you should put that abstracted away in some sort of hardware abstraction layer. Then make sure you have a defined GUI or GUIs and a game plan for how those GUIs should interact, and what problems they're solving. Then make sure that you lay out your test scripts in a way that's maintainable and scalable. So having decoupling the actual tests from the limit collection is a really good way to do that. And sorry, I lost my train of thought. If you do decouple the test sequences from your, if you decouple the test gathering, the measurements from your actual test limits, it allows you to also separate and change tests and affect all of your limits if you need to, right? So if the way that I collect data always changes, or sorry, if the way that I collect data for a specific test, the API call changes to the DUT, I could just change it in that one spot, and then all my other test sequences still work. So, well, Rob, I will get to your question in just a second once I finish up this whole train of thought, but that's a fantastic question. After we've done our test scripts or during test scripts, we really need to think about how are we going to store our data, what reporting are we going to do, and a lot of that should be done part of our first phase. But creating a report from the beginning is going to really benefit you in helping helping scope not creep, right? So like if you give them a report, a mock-up report from the beginning, it's going to allow you to hold them to it, essentially. And then finally, have a plan for deployment. How are you going to deploy this? How are you going to make sure that it doesn't change? If I start working on another system, how am I going to reuse code? That kind of stuff. So that is, those are all the pieces that I would recommend thinking about within your test system. That's going to wrap up the main core part of our presentation. We're going to talk about questions from here on out. I have a feedback form. Actually, can I copy this link live? Oh, there it goes. There goes my slide deck. I'll have Jason post the link in the chat, or you can scan the QR code. Jason answered Rob's question, but using test stand for sequencing, what's the major benefit of using this versus other applications? Jason said test stand is very robust sequencer and has a ton of great debugging features that give you a really good insight into exactly what's going on during a test sequence. Additionally, test stand is very expandable and customizable through plugins, overrides, and etc., which is why we use it extensively at TestRact. Jason's absolutely correct. It's really hard to build a good test sequencer. I would bet that most of you have used a homebrewed test sequencer and you run into a lot of problems. Test stand is extremely robust, and one of the benefits of test stand is it supports, it has adapters, so you can call different pieces of code. So you can call Python, and you can call LabVIEW or C. I think C, definitely C#. And so it's really hard to build one. It costs a lot of money to build one. And so it's really beneficial just to use an off-the-shelf one. Use one that's good. There's some competitors to test stand as well, like OpenTap and I think AT Easy. So those are some things that you can also look into. Yep, Jason's correct. Test stand takes care of the whole thing for you, or a lot of things for you. Reporting, parallelization, multiple socket handling. It's got different process models for parallel or sequential models, or batch, that kind of stuff. It's really good. Any other questions? Yeah, I would actually like to know how many of you have your own hardware abstraction layer. I feel like that's, I've seen it a lot in the industry, which is good. That matters a lot to me. Good. Rob, you should definitely join our HAL presentation. I think if you have a HAL, you'll take some good ideas from it. From it. Okay, looks like we don't have a ton of questions. I'm here until 11, so I'll hang out. Jason, the rest of the TestRact team will hang out.
Yep. So feel free to ask any questions in the chat. And if you have any other things that you'd like us to make for future webinars too, that would also be very handy. We're just getting started with webinars, and we have a lot of expertise and a lot of people at Tesseract. We also have partners like NI who can bring additional expertise that we can bring on. So let us know if there's any specific things you would like to know in the future or anything like that. Again, check that feedback form and let us know if you have questions or any issues or anything like that. We are really glad to have you here, and we're glad it's great to see some of those questions. People thinking about that kind of stuff. Like before I joined Tesseract, I'd been working in test and measurement for a long time, and I'd never really used a how. And now that I see the benefits of it, I'm surprised. And so things like that, hopefully that's one of the things you can take away, that there is valuable methods you can use to make your test systems much easier. Again, thank everybody for attending, and we will be on chat if you have any further questions.